What if everything you thought you knew about time was wrong? What if time isn't a straight line, but something far more mysterious, bending and twisting in ways that defy our everyday understanding? Time is one of the most fundamental aspects of our existence, yet it remains one of the greatest mysteries of the universe. From the way it slows down near massive objects to the mind-bending idea that it might not even exist at the speed of light, time is anything but simple. In this video, we're diving deep into the cosmos to uncover 30 mind-blowing facts about time that will challenge everything you thought you knew. Get ready to explore how black holes warp time, why time might have begun with the Big Bang, and even whether time travel could one day be possible. By the end of this journey, you'll see time in a whole new light, and you might just question the very nature of reality itself. So, are you ready to unravel the secrets of time in the universe? Let's begin. Now, let's dive into our first mind-bending fact, time dilation. This phenomenon is one of the most fascinating predictions of Einstein's theory of relativity, and it completely changes how we think about time. According to Einstein, time isn't a fixed, unchanging thing. It's flexible. It can stretch, slow down, or speed up depending on where you are and how fast you're moving. For example, imagine two identical clocks. If one clock is placed on Earth and the other is sent into space, the clock in space will actually tick slower than the one on Earth. This isn't science fiction, it's real science. Astronauts on the International Space Station experience this firsthand because they're moving at incredibly high speeds and are farther from Earth's gravity. Time for them passes just a tiny bit slower than it does for us on the ground. Over months or years, this difference adds up, meaning astronauts technically age slower than people on Earth. But it's not just about speed. Massive objects like planets and stars also warp time. The closer you get to a massive object, the slower time moves. This is because massive objects bend the fabric of space-time, a concept that combines space and time into a single, interconnected framework. So the next time you look at a clock, remember time isn't as straightforward as it seems. It's a dynamic, ever-changing force that bends to the rules of the universe. And this is just the beginning. Our journey into the mysteries of time is only getting started. Now, let's take a closer look at one of the most intriguing thought experiments in physics, the twin paradox. Imagine two identical twins. One decides to stay on Earth, living a normal life, while the other embarks on a journey through space at speeds close to the speed of light. According to Einstein's theory of relativity, time doesn't pass the same way for both twins. The twin traveling at near light speed would experience time much more slowly compared to the twin who stayed on Earth. When the spacefaring twin returns after what feels like a few years to them, they might find that decades or even centuries have passed on Earth. This isn't just a wild idea, it's a real consequence of time dilation. The faster you move through space, the slower time moves for you relative to someone who isn't moving as fast. This paradox isn't just a fascinating thought experiment, it has real implications for the future of space travel. If humans ever develop the technology to travel at such incredible speeds, astronauts could potentially journey to distant stars and return to an Earth that has aged far more than they have. It's a concept that challenges our understanding of time and raises profound questions about the nature of reality. What would it mean to outpace time itself? And how would humanity adapt to such a future? The twin paradox doesn't just bend our minds, it opens the door to a universe where time is no longer the constant we once thought it was. And as we continue to explore the mysteries of time, we'll uncover even more astonishing truths about the cosmos. Now, let's push the boundaries of our imagination even further and step into a world where time itself seems to vanish. At the speed of light, something truly extraordinary happens. Time stops. Yes, you heard that right. For a photon, a particle of light, time doesn't exist. From the moment it's emitted to the moment it's absorbed, a photon experiences no passage of time at all. To us, light travels across vast distances, taking years or even billions of years to reach us from distant stars. But for the photon, that journey is instantaneous. It's as if the entire trip happens in a single, timeless moment. This mind-bending concept comes straight from Einstein's theory of relativity, which tells us that as an object approaches the speed of light, time slows down relative to an outside observer. But at the speed of light itself, time doesn't just slow, it stops completely. This raises some fascinating questions about the nature of reality. If time doesn't exist for light, does that mean the universe is fundamentally timeless from the perspective of a photon? And what does this tell us about the relationship between time, space, and motion? It's a reminder that our everyday experience of time is just one piece of a much larger, more mysterious puzzle. As we continue to explore the universe, we're constantly reminded that the rules we take for granted here on Earth don't always apply out there. The idea that time can stop at the speed of light challenges us to rethink what we know about existence itself. And as we peel back the layers of this cosmic mystery, we're left with more questions than answers, questions that might just lead us to a deeper understanding of the universe and our place within it. Now let's dive into one of the most extreme examples of time's flexibility: black holes. These cosmic giants don't just bend the rules of time, they shatter them. Imagine approaching a black hole where gravity is so intense that not even light can escape. As you get closer to the event horizon, the boundary around a black hole, something strange happens to time. From the perspective of someone watching from a safe distance, your clock would appear to slow down. The closer you get to the event horizon, the slower time seems to crawl until it almost stops entirely. This is known as gravitational time dilation, a direct consequence of Einstein's theory of general relativity. But here's where it gets even weirder. If you were to cross the event horizon and approach the singularity at the center of the black hole, time would stop completely. From an outside observer's point of view, you would appear frozen in time, forever suspended at the edge of the black hole. It's as if the universe itself hits the pause button. This bizarre phenomenon raises profound questions about the nature of time and reality. What does it mean for time to stop? And what happens to the laws of physics in a place where time no longer flows? Black holes challenge our understanding of the universe in ways that are both thrilling and unsettling. They remind us that time isn't just a steady, unchanging force, it's a dynamic, malleable fabric that can be stretched, twisted, and even brought to a standstill under the right conditions. As we continue to explore these cosmic enigmas, we're forced to confront the limits of our knowledge and the mysteries that lie beyond. And with each discovery, we inch closer to unraveling the true nature of time itself. Now, shifting our focus from the mind-bending distortions of time near black holes, let's journey back to the very beginning, the Big Bang. This monumental event isn't just the birth of our universe, it's also the starting point of time itself. Before the Big Bang, there was no time as we know it. No seconds, no minutes, no years, just an incomprehensible state where the laws of physics as we understand them didn't apply. This raises one of the most profound questions in science. What existed before time began? The truth is, we don't have a definitive answer. Some theories suggest that the concept of before doesn't even make sense in this context because time itself didn't exist. It's like asking what's north of the North Pole. There's no meaningful way to answer because the framework for the question breaks down. Other theories propose that our universe might be part of a larger multiverse, where time flows differently in other realms, or that the Big Bang was just one event in an endless cycle of cosmic expansion and contraction. These ideas push the boundaries of our understanding, challenging us to think beyond the limits of time and space. The Big Bang reminds us that time isn't just a backdrop to the universe, it's a fundamental part of it, woven into the very fabric of reality. And as we continue to explore these mysteries, we're left with more questions than answers, each one leading us deeper into the enigma of existence. What does it mean for time to have a beginning? And if time had a start, could it also have an end? These are the kinds of questions that keep scientists and philosophers awake at night, and they remind us just how much we still have to learn about the universe and our place within it. Now, let's take a leap into the future literally. Time travel to the future isn't just the stuff of science fiction. It's a real possibility grounded in the science of time dilation. Thanks to Einstein's theory of relativity, we know that time doesn't tick at the same rate for everyone. If you're moving really fast or hanging out in a strong gravitational field, time slows down for you compared to someone in a different situation. This means that, in a way, you're already time traveling into the future, just very, very slowly. But what if we could speed that up? One of the most famous experiments proving this is the Hayfel-Keating experiment. In the early 1970s, scientists flew atomic clocks on airplanes traveling in opposite directions around the Earth. When they compared these clocks to ones that stayed on the ground, they found that the clocks on the planes had ticked slightly slower. The difference was tiny, just a few billionths of a second, but it was enough to show that time dilation is real. Now, imagine scaling this up. If we could build a spacecraft capable of traveling close to the speed of light, time for the astronauts on board would slow down dramatically compared to people on Earth. A journey that feels like a few years to the crew could mean decades or even centuries have passed back home. This isn't just theoretical future space missions, especially those aiming to explore distant stars could make this a reality. But here's the catch: while traveling to the future is theoretically possible, there's no way to come back. Once you've jumped ahead, you're stuck there. Still, the idea opens up incredible possibilities. What if we could send explorers to distant galaxies and have them return to an Earth that's centuries older? Or what if we could witness the evolution of humanity from a distant future? These questions remind us that time, as mysterious as it is, holds the key to unlocking some of the universe's greatest secrets. And as we push the boundaries of science and technology, the future might be closer than we think. Now, let's turn the clock backward, because while traveling to the future is fascinating, the idea of journeying into the past is where things get truly mind-bending. Time travel to the past isn't just a staple of science fiction. It's a concept that physicists have seriously explored, even if it remains purely theoretical for now. One of the most intriguing ideas comes from Einstein's theory of relativity, which suggests that certain conditions in space-time could allow for backward time travel. Enter wormholes, hypothetical tunnels through space-time that could connect two distant points or even two different times. If a wormhole could be stabilized, it might serve as a shortcut not just through space but through time itself. But wormholes aren't the only possibility. Another theoretical pathway involves something called closed time-like curves. These are paths through space-time that loop back on themselves, essentially allowing an object or person to return to their own past. While this sounds like something straight out of a time travel movie, it's a concept that emerges from the math of general relativity. However, there's a catch. Creating or finding such a curve would require conditions that are far beyond our current understanding or even our technological capabilities. Of course, time travel to the past isn't without its problems. One of the biggest hurdles is the grandfather paradox. Imagine traveling back in time and accidentally preventing your grandparents from meeting. If they never meet, your parents, and by extension you, would never be born. But if you were never born, how could you have traveled back in time to interfere in the first place? This paradox highlights the logical inconsistencies that arise when we try to imagine altering the past. Some physicists have proposed solutions to these paradoxes, like the idea of parallel universes. In this scenario, traveling to the past wouldn't change your own timeline, but would instead create a new, alternate reality where the changes take place. This way, the original timeline remains intact and the paradox is avoided. While this might sound like science fiction, it's a serious area of study in theoretical physics. The idea of traveling to the past raises profound questions about cause and effect, free will, and the nature of reality itself. Could we ever truly change the past, or would the universe find a way to preserve the timeline as we know it? These questions remind us that time, as much as we try to understand it, remains one of the universe's greatest mysteries. And as we continue to explore the possibilities, we might just find that the past holds as many secrets as the future. Now, let's shift our focus to a concept that might seem obvious but is anything but simple: the arrow of time. Why does time only move forward? Why can't we rewind the universe like a video and watch events unfold backward? The answer lies in a fundamental principle of physics called entropy. Entropy is a measure of disorder in a system, and it's one of the few things in the universe that always increases over time. Think of it like this: if you drop a glass and it shatters, the pieces scatter in every direction. That's an increase in entropy. But have you ever seen a shattered glass spontaneously reassemble itself? Of course not. That's because entropy only moves in one direction toward greater disorder. This irreversible increase in entropy is what gives time its direction, or its arrow. It's why we remember the past but not the future, and why cause always precedes effect. Without entropy, time would lose its forward momentum, and the universe would become a chaotic mess where events could happen in any order. But here's where it gets even more fascinating. The arrow of time isn't just about broken glasses or messy rooms. It's deeply tied to the very fabric of the universe. At the moment of the Big Bang, the universe was in a state of incredibly low entropy, a highly ordered state. As the universe expanded and cooled, entropy began to increase, setting the stage for the arrow of time we experience today. Some scientists speculate that if the universe were to eventually collapse in a big crunch, entropy might reverse and time could theoretically run backward. But for now, the arrow of time points firmly in one direction, shaping everything from the formation of galaxies to the beating of our hearts. So, the next time you wonder why you can't go back and change the past, remember, it's not just a quirk of human experience. It's a fundamental law of the universe, written in the language of entropy. And as we continue to explore the mysteries of time, we might just find that its arrow is one of the most profound forces shaping our reality. Now, let's take a journey beyond Earth and explore how time behaves on other planets. You might think a day is always 24 hours, but out there in the cosmos, time can feel like it's playing by a completely different set of rules. This is because the way time passes is deeply influenced by a planet's gravity and its speed of rotation. Take Venus, for example. A single day on Venus, meaning the time it takes for the planet to rotate once on its axis, is actually longer than its entire year. That's right, a Venusian day lasts about 243 Earth days, while its year, or the time it takes to orbit the Sun, is only about 225 Earth days. So, if you were standing on Venus, you'd experience a sunrise only once every 243 days, but you'd celebrate your birthday twice in that same period. But Venus isn't the only planet with a quirky sense of time. On Jupiter, the largest planet in our solar system, a day flies by in just under 10 hours. That's because Jupiter spins incredibly fast despite its massive size. Meanwhile, on Mercury, a day lasts about 59 Earth days, but its year is only 88 Earth days long. This means Mercury experiences just 1.5 days in a single year. And then there's Mars, often called Earth's twin in terms of time. A Martian day, or Sol, is just slightly longer than an Earth day, lasting about 24 hours and 37 minutes. But even here, time isn't exactly the same. Mars's thinner atmosphere and weaker gravity mean that if you were to live there, you'd age just a tiny bit faster than you would on Earth. These differences in time aren't just fun facts, they're a reminder of how the universe operates on scales that can feel almost alien to us. gravity, speed, and even the shape of a planet's orbit all play a role in shaping how time flows. So the next time you glance at a clock, remember, out there among the stars, time is bending, stretching, and twisting in ways that challenge our earth-bound understanding of reality. And speaking of bending time, let's dive into another mind-bending concept, the age of the universe itself. How do scientists measure something as vast as cosmic time? Stay tuned because that's up next. Now, let's zoom out from the planets and take a look at the grandest scale of time imaginable, the age of the universe itself. How do scientists even begin to measure something as vast as 13.8 billion years? It's a question that takes us to the very edge of our understanding of time and space. To figure out the universe's age, researchers rely on a few key pieces of evidence, one of the most important being the cosmic microwave background radiation. This faint glow, often called the afterglow of the Big Bang, is the oldest light in the universe. It's like a snapshot of the cosmos when it was just 380,000 years old, and it holds clues about how the universe has expanded over time. By studying this radiation, scientists can trace the universe's growth and calculate how long it's been since the Big Bang. Another method involves observing the oldest stars and galaxies. By measuring their distance and brightness, astronomers can estimate how long it took for these celestial objects to form and evolve. These observations align remarkably well with the data from the cosmic microwave background, giving us a consistent picture of the universe's age. But what does 13.8 billion years really mean in the context of time? To put it into perspective, imagine compressing the entire history of the universe into a single calendar year. The Big Bang would occur at midnight on January 1st, and our modern era would be just the last few seconds of December 31st. In this cosmic calendar, the Earth doesn't even form until early September, and humans appear only in the final moments of the year. It's a humbling reminder of just how young we are in the grand timeline of existence. This vast timescale also raises fascinating questions about the future. If the universe is already 13.8 billion years old, how much longer will it last? Will it continue expanding forever, or will it eventually collapse back in on itself? These are mysteries that scientists are still working to unravel, but one thing is certain. The age of the universe reminds us that time on a cosmic level is almost beyond comprehension. And speaking of time's mysteries, let's turn our attention to how time behaved in the early universe, when the rules of physics were far different from what we know today. That's coming up next. Now, let's take a step back, way back to the very beginning, when the universe was just a fraction of a second old. This is where time itself becomes a mystery, because in the early universe, the rules of physics as we know them didn't apply. Instead, everything was governed by conditions so extreme that even time behaved in ways we can barely comprehend. This period, known as the Planck epoch, is the earliest moment we can theorize about, lasting from the Big Bang until about 10 to the power of negative 43 seconds. To put that into perspective, it's a timescale so short that it's almost impossible to imagine. During this fleeting instant, the universe was unimaginably hot and dense, and the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, all-encompassing force. But here's where things get even stranger. At such extreme energies and densities, the very fabric of space-time was subject to quantum fluctuations. This means that time itself didn't flow in the smooth, continuous way we experience today. Instead, it was more like a chaotic, jittery dance, with moments that might not even have followed a clear sequence. This is where the concept of quantum gravity comes into play, a theoretical framework that attempts to reconcile the laws of quantum mechanics with Einstein's theory of general relativity. Quantum gravity suggests that, in the Planck epoch, spacetime itself might have been granular, made up of tiny, discrete units rather than the smooth continuum we're familiar with. Imagine time as a series of individual frames in a film, each one distinct and separate rather than a flowing river. This idea challenges our everyday understanding of time and raises profound questions about the nature of reality itself. What's even more fascinating is that during this epoch, the very concept of before and after might not have existed in the way we think of them. Without a clear arrow of time, events in the early universe could have unfolded in ways that defy our intuition. It's a realm where the familiar rules of cause and effect break down, and where time itself becomes a puzzle waiting to be solved. As we move forward in our exploration of time's mysteries, let's shift our focus to how time interacts with the strange and unpredictable world of quantum mechanics. That's where things get even more mind-bending. Now, let's step into the bizarre and fascinating world of quantum mechanics, where time takes on a role that's as puzzling as it is profound. In this realm, the rules of the universe seem to bend, twist, and sometimes even break, leaving us with more questions than answers. One of the most mind-bending aspects of quantum mechanics is how it challenges our understanding of time itself. At the heart of this mystery is a phenomenon called quantum superposition. This is the idea that particles, like electrons or photons, can exist in multiple states at once until they're observed. Imagine flipping a coin. In our everyday world, it's either heads or tails. But in the quantum world, that coin could be both heads and tails simultaneously, spinning in a kind of limbo until someone looks at it. This strange behavior isn't just a quirk of tiny particles, it has profound implications for how we think about time. In the quantum realm, time doesn't always flow in the straightforward, linear way we're used to. Instead, it can become fuzzy, with events happening in a kind of probabilistic haze. For example, a particle might exist in a superposition of states across different moments in time, meaning it's not just in one place at one time, it's in multiple places across multiple times. This idea is so counterintuitive that even the greatest minds in physics, like Albert Einstein, found it hard to accept, but here's where it gets even stranger. The act of observation itself plays a crucial role in shaping reality. When we measure or observe a quantum system, it collapses from its superposition of states into a single, definite state. This means that, in a way, time itself might be influenced by observation. It's as if the universe waits until we look at it before deciding how things should be. This leads us to one of the most intriguing questions in physics. Does time exist independently of the observer, or is it somehow tied to our perception? Quantum mechanics doesn't give us a clear answer, but it does suggest that time might be far more flexible and subjective than we ever imagined. As we continue to explore the mysteries of time, let's turn our attention to another mind-bending concept, the end of time itself. What happens when time, as we know it, ceases to exist? That's where our journey takes us next. Now, let's venture into one of the most profound and unsettling questions in cosmology. What happens when time itself comes to an end? The idea of time ceasing to exist might sound like science fiction, but according to some of the leading theories in physics, it's a very real possibility. One of the most widely discussed scenarios is the heat death of the universe. This theory suggests that, as the universe continues to expand, all the stars will eventually burn out, galaxies will drift apart, and the cosmos will become a cold, dark, and lifeless void. In this state, no energy will be left to sustain any form of activity, and time, as we understand it, will lose its meaning. Without events or changes to mark its passage, time would essentially stop. It's a chilling thought, a universe frozen in an eternal, unchanging state. But there's another possibility, the Big Crunch. This theory proposes that, instead of expanding forever, the universe could one day stop expanding and begin to collapse back in on itself. Imagine all the galaxies, stars, and planets being pulled together by gravity, eventually merging into a single, infinitely dense point, a reverse of the Big Bang. In this scenario, time would also come to an end, as the universe would cease to exist in any recognizable form. Both of these theories raise fascinating questions about the nature of time. Is time something that exists independently of the universe, or is it simply a byproduct of change and motion? If the universe reaches a state where nothing changes, does time still have a purpose? These are questions that challenge not only our understanding of physics, but also our very perception of reality. As we ponder these cosmic possibilities, it's worth remembering that the end of time, if it ever happens, is unimaginably far in the future. But exploring these ideas helps us appreciate just how strange and mysterious the universe truly is. And with that, let's turn our attention to another groundbreaking concept: time crystals, a new phase of matter that defies our traditional understanding of time itself. Now, let's shift our focus to something that sounds like it's straight out of a science fiction novel, but is very much a reality in the world of physics: time crystals. Unlike ordinary crystals, which have a repeating structure in space, think of the geometric patterns in diamonds or snowflakes. Time crystals have a structure that repeats in time. This means they exhibit periodic motion, not because of external forces, but as a fundamental property of their existence. It's as if they're dancing to a rhythm set by the universe itself. The concept of time crystals was first proposed in 2012 by Nobel laureate Frank Wilczek, and it took the scientific community by storm. What makes them so fascinating is that they break one of the most fundamental assumptions in physics: the idea that a system in its lowest energy state or ground state should be static. Time crystals, however, are in perpetual motion even in their ground state, defying our traditional understanding of how matter behaves. So, how do they work? Imagine a ring of particles that, instead of staying still, continuously flip their spins in a repeating cycle without any energy input. This cyclical behavior isn't driven by external forces, but is an intrinsic property of the system. It's like a clock that ticks forever without needing to be wound. The discovery of time crystals has opened up a whole new frontier in physics. Scientists have already created them in controlled laboratory settings using systems like chains of ions or superconducting qubits. These experiments have not only confirmed their existence but also hinted at their potential applications. For instance, time crystals could revolutionize quantum computing by providing stable, error-resistant systems for processing information. They might also help us better understand the nature of time itself, offering clues about how time emerges from the quantum realm. But perhaps the most mind-bending implication of time crystals is what they tell us about the universe. They challenge our understanding of equilibrium and symmetry, suggesting that there are states of matter we've only just begun to explore. Could there be other exotic phases of matter waiting to be discovered? And what does this mean for our understanding of the fundamental laws of physics? As we continue to unravel the mysteries of time crystals, one thing is clear: they remind us that the universe is far stranger and more wondrous than we ever imagined. And with that, let's move on to another fascinating aspect of time: how it's perceived by astronauts in the vast emptiness of space. Now, let's take a step into the shoes of astronauts and explore how time feels when you're floating in the vast emptiness of space. Time perception in space is a fascinating topic, and it's not just about clocks ticking differently. It's about how the human mind experiences time when removed from the familiar rhythms of Earth. In the microgravity environment of space, astronauts often report that time seems to flow differently. Without the usual cues like sunrise and sunset or the pull of gravity, their internal clocks can become disoriented. Imagine living in a place where up and down don't exist, and the day-night cycle is replaced by artificial lighting. This can make hours feel longer or shorter than they actually are, depending on the individual. Studies have shown that isolation and confinement also play a significant role in altering time perception. On Earth, our daily routines like eating, sleeping, and working help anchor our sense of time. But in space, these routines are disrupted. Astronauts on the International Space Station, for example, experience 16 sunrises and sunsets every 24 hours due to their rapid orbit around Earth. This constant shift can make it harder to maintain a regular sleep schedule, further distorting their perception of time. Interestingly, research has revealed that astronauts often underestimate the passage of time during long missions. In one study, participants were asked to estimate intervals of time while in space, and many consistently thought less time had passed than actually had. This phenomenon, sometimes called time compression, could have serious implications for future deep space missions, where accurate timekeeping will be crucial for navigation, communication, and even mental health. The effects of altered time perception aren't just limited to the mind, they can impact the body too. Disrupted circadian rhythms, the internal processes that regulate our sleep-wake cycles, can lead to fatigue, reduced cognitive performance, and even mood changes. Scientists are actively studying these effects to develop better strategies for helping astronauts maintain a healthy sense of time during extended missions. As we look toward the future of space exploration, understanding how time is perceived in space will be essential. Whether it's a journey to Mars or beyond, ensuring that astronauts can accurately gauge time and stay mentally sharp will be key to the success of these missions. And with that, let's turn our attention to another cosmic mystery: how dark matter might influence the very fabric of time itself. Now, let's shift our focus to one of the most mysterious forces in the cosmos, dark matter, and its intriguing relationship with time. While dark matter doesn't emit light or energy, making it invisible to our telescopes, its gravitational influence is undeniable. But could this enigmatic substance also affect the very fabric of time itself? Scientists believe that dark matter makes up about 27% of the universe, far outweighing the ordinary matter we can see. Its gravitational pull shapes galaxies, clusters, and even the large-scale structure of the cosmos. But here's where it gets fascinating: dark matter's immense gravitational influence might also warp spacetime, the very framework in which time exists. One theory suggests that dark matter could create regions where time flows differently. Imagine areas of the universe where dark matter is densely concentrated. In these regions, the intense gravitational field could slow down time, much like how time slows near a black hole. While we haven't directly observed this effect, it's a compelling idea that challenges our understanding of time's uniformity across the universe. Dark matter also plays a crucial role in the universe's expansion. As the cosmos stretches, dark matter's gravitational pull helps shape the rate at which galaxies move apart. Some researchers speculate that this expansion could influence the flow of time on a cosmic scale. If the universe's expansion accelerates, as current observations suggest, could time itself stretch or slow in response? These questions remain unanswered, but they open up thrilling possibilities for future discoveries. Another intriguing angle is the potential connection between dark matter and the arrow of time, the one-way direction in which time flows. Could dark matter's gravitational effects influence entropy, the measure of disorder that defines the arrow of time? While this is still speculative, it's a fascinating area of research that could reshape our understanding of time's fundamental nature. As we continue to explore the mysteries of dark matter, its potential impact on time remains a tantalizing puzzle. From warping spacetime to influencing the universe's expansion, dark matter challenges us to rethink not just what we know about the cosmos, but also how we perceive time itself. And with that, let's move on to another mind-bending concept: how multiple universes might each have their own unique timelines. Now, let's venture into one of the most mind-bending ideas in modern physics, the multiverse theory. Imagine not just one universe, but countless others, each with its own unique set of physical laws and timelines. This concept suggests that our universe might be just one bubble in an infinite cosmic ocean, where time itself could behave in ways we can barely comprehend. In the multiverse framework, time might not flow uniformly across all universes. Some could experience time at a faster rate, while others might have it moving slower or even in reverse. Picture a universe where time loops endlessly, or another where it branches into infinite possibilities with every decision made. These ideas challenge our understanding of time as a linear, one-way progression and open up a universe of possibilities literally. One fascinating aspect of multiverse theory is the idea of alternate timelines. In some universes, events might unfold differently than they do in ours. For example, a universe where dinosaurs never went extinct, or one where humanity never evolved. These alternate timelines raise profound questions about the nature of reality. If time can branch into infinite paths, does that mean every possible outcome exists somewhere in the multiverse? Another intriguing possibility is that the laws of physics governing time could vary between universes. In some, time might be a rigid, unchanging force, while in others it could be fluid and malleable. This variability could mean that concepts like cause and effect, or even the arrow of time, might not apply universally. It's a thought that stretches the limits of our imagination and forces us to reconsider what we think we know about time. The multiverse theory also ties into quantum mechanics, where particles can exist in multiple states until observed. Some interpretations suggest that every quantum event spawns a new universe, creating an ever-expanding web of realities. If this is true, then time itself might be a branching, ever-evolving phenomenon, with each universe carving its own unique path through the cosmic tapestry. While the multiverse remains a speculative idea, it's a powerful tool for exploring the nature of time and reality. It challenges us to think beyond the confines of our own universe and consider the infinite possibilities that might exist beyond. And with that, let's turn our attention to another profound question: whether time exists independently or is a construct of human consciousness. Now, let's shift our focus to a question that bridges the gap between science and philosophy. Does time exist independently, or is it a construct of our own consciousness? This idea challenges us to think about whether time is an objective feature of the universe or something our minds create to make sense of the world around us. From a philosophical perspective, some argue that time is a mental framework. Think about how we experience time. It feels linear, moving from past to present to future. But is that flow real, or is it just how our brains organize memories and expectations? For example, when you're deeply engrossed in an activity, time seems to fly by, but when you're bored, it drags endlessly. This subjective experience of time suggests that our perception plays a huge role in how we understand it. On the other hand, physics tells us that time is woven into the fabric of the universe. Einstein's theory of relativity shows that time is part of space-time, a four-dimensional structure that can bend and stretch. This implies that time exists independently of us as a fundamental aspect of reality. But here's the twist: quantum mechanics introduces uncertainty into the mix. At the smallest scales, particles don't follow strict timelines. They can exist in multiple states until observed, blurring the line between past, present, and future. Some theories even suggest that consciousness itself might influence how time behaves. The idea of the observer effect in quantum mechanics hints that the act of observing could collapse possibilities into a single timeline. If that's true, does our awareness shape time, or does time shape our awareness? It's a chicken and egg problem that continues to puzzle scientists and philosophers alike. This debate isn't just academic, it has real implications for how we understand reality. If time is a construct of consciousness, then our perception of the universe might be deeply personal, shaped by our individual experiences. But if time is an independent force, it raises questions about how we fit into the grand cosmic order. As we ponder these ideas, it's clear that time is more than just a ticking clock. It's a mystery that connects the physical world with the inner workings of our minds. And with that, let's move on to explore how time behaves in one of the most extreme environments imaginable, a perfect vacuum. Now, let's step into the strange and silent world of a perfect vacuum, a space completely devoid of matter where even air molecules are absent. You might think that in such an empty environment, time would behave in the simplest, most straightforward way possible. But as it turns out, even in a vacuum, time has some surprising tricks up its sleeve. In a perfect vacuum, time doesn't just tick away uniformly. Instead, it interacts with the very fabric of space-time in ways that challenge our everyday understanding. One of the most fascinating phenomena that reveal this is the Casimir effect. Named after the physicist Hendrik Casimir, this effect occurs when two uncharged, parallel metal plates are placed extremely close to each other in a vacuum. Despite the absence of any external forces, the plates are drawn together by an invisible force. What's happening here? In the vacuum, empty space isn't truly empty. Quantum mechanics tells us that even in a vacuum, particles and antiparticles constantly pop in and out of existence. These fleeting particles, known as virtual particles, create tiny fluctuations in energy. When the plates are brought close together, the space between them restricts the types of virtual particles that can exist there, while the space outside the plates remains unaffected. This imbalance creates a pressure difference pulling the plates together. The Casimir effect isn't just a curious laboratory observation, it's a window into the nature of spacetime itself. It shows us that even in the absence of matter, spacetime is alive with activity. These quantum fluctuations suggest that time and space are not static backdrops but dynamic, ever-changing entities. This has profound implications for our understanding of time. If space-time can fluctuate in a vacuum, then time itself might not be as rigid as we once thought. It hints at a universe where time is more fluid, influenced by the underlying quantum fabric of reality. So, the next time you think of a vacuum as just empty space, remember, it's anything but empty. It's a realm where time and space dance to the tune of quantum mechanics, revealing the hidden complexities of the universe. And with that, let's turn our attention to another cosmic phenomenon that bends our understanding of time: gravitational waves. Now, let's dive into the ripples that shake the very fabric of the universe: gravitational waves. These are not just ordinary waves, they are disturbances in spacetime itself, created by some of the most violent and energetic events in the cosmos. Imagine spacetime as a calm lake and gravitational waves as the ripples that spread across its surface when a massive object, like a black hole or neutron star, collides with another. These ripples carry with them secrets about the nature of time and the universe itself. Gravitational waves were first predicted by Albert Einstein over 100 years ago as part of his theory of general relativity. But it wasn't until 2015 that scientists finally detected them directly, using incredibly sensitive instruments called interferometers. These devices, like the Laser Interferometer Gravitational Wave Observatory, or LIGO, measure tiny distortions in spacetime caused by passing gravitational waves. The detection was a monumental achievement, confirming Einstein's prediction and opening a new way to observe the universe. So, what do these ripples tell us about time? Gravitational waves are essentially messengers from the distant cosmos, carrying information about the events that created them. When two black holes collide, for example, the resulting gravitational waves encode details about the masses of the black holes, their speeds, and even the shape of spacetime around them. By studying these waves, scientists can piece together the timeline of these cataclysmic events, effectively listening to the universe's history. But there's more. Gravitational waves also reveal how spacetime behaves under extreme conditions. They show us that spacetime isn't just a static stage where events unfold. It's a dynamic, flexible entity that can stretch, compress, and ripple. This means that time itself is not a fixed, unchanging backdrop. Instead, it's intertwined with space, bending and warping in response to massive objects and energetic events. The detection of gravitational waves has given us a new tool to explore the universe. It's like adding a new sense to our cosmic perception. Before, we relied on light to study the cosmos. Now we can also hear it through the vibrations of space-time. This has already led to groundbreaking discoveries, such as the first observation of a neutron star collision, which produced both gravitational waves and light, offering a multi-messenger view of the event. Gravitational waves remind us that time is not just a ticking clock. It's a dynamic, interconnected part of the universe's fabric. They challenge us to rethink our understanding of time, showing us that it's not just something we measure, but something that can be shaped and influenced by the cosmos itself. And with that, let's turn our attention to another fascinating connection: time and the speed of light. Now, let's shift our focus to one of the most fundamental relationships in the universe, the connection between time and the speed of light. Light, as we know it, is not just the fastest thing in the cosmos, it's also the ultimate speed limit. Nothing can travel faster than light, and this simple fact has profound implications for how we understand time and causality. Imagine this: light travels at a constant speed of about 300,000 kilometers per second in a vacuum. This speed is so consistent that it forms the backbone of Einstein's theory of relativity. But here's where it gets fascinating: because light's speed is constant, it doesn't change regardless of how fast you're moving or where you are in the universe. This constancy means that time itself must adjust to keep the speed of light unchanged. This is where time dilation comes into play. Let's break it down. If you were to travel close to the speed of light, time would slow down for you relative to someone standing still. This isn't just a theoretical idea. It's been proven through experiments with atomic clocks on fast-moving airplanes and satellites. The faster you go, the more time slows down for you compared to someone at rest. This phenomenon shows that time isn't absolute, it's relative, and it's deeply tied to the speed of light. But the relationship between time and light goes even deeper. Light's constant speed also shapes our understanding of causality, the idea that cause must come before effect. Because nothing can travel faster than light, information about events can't spread instantaneously. This means that the order of events is preserved across the universe. For example, if a star explodes in a distant galaxy, we won't see the explosion until the light from it reaches us, no matter how powerful the event was. This delay ensures that cause and effect remain intact, even across vast cosmic distances. This connection between light and time also raises intriguing questions about the nature of reality. If you could somehow travel at the speed of light, time would effectively stop for you. Photons, the particles of light, don't experience time at all from their perspective. For them, the moment they're emitted is the same moment they're absorbed, no matter how far they travel. This mind-bending idea challenges our everyday experience of time as a steady, flowing river. The speed of light isn't just a number, it's a cosmic rule that governs how time behaves and how events unfold in the universe. It's a reminder that time isn't just something we measure with clocks. It's a dynamic, interconnected part of the fabric of reality. And as we continue to explore this relationship, we uncover even more about the mysteries of time itself. With that in mind, let's turn our attention to another cosmic phenomenon: the expansion of the universe and how it influences the passage of time. Now, let's take a closer look at how the universe's expansion plays a role in shaping time itself. The universe isn't static, it's constantly stretching, and this expansion has a direct impact on how time flows. This idea might sound abstract, but it's one of the most profound ways our understanding of time has evolved over the past century. At the heart of this concept is the Hubble constant, a key piece of the cosmic puzzle. Named after the astronomer Edwin Hubble, this constant measures the rate at which the universe is expanding. Think of it like this: imagine the universe as a loaf of raisin bread baking in an oven. As the bread rises, the raisins representing galaxies move farther apart from one another. The Hubble constant tells us how fast those raisins are spreading apart. But here's the twist: this expansion isn't just about space, it's also about time. As space stretches, it affects the passage of time in subtle but significant ways. For instance, light traveling through an expanding universe gets stretched along with space, a phenomenon known as redshift. This stretching of light means that the farther away a galaxy is, the longer its light takes to reach us. In a sense, we're looking back in time when we observe distant galaxies, seeing them as they were billions of years ago. This cosmic time machine allows us to study the universe's history, but it also shows how time itself is intertwined with the fabric of space. The expansion of the universe also raises fascinating questions about the future of time. If the universe continues to expand at an accelerating rate, as current observations suggest, distant galaxies will eventually move so far away that their light will never reach us. This means that in the distant future, observers in our galaxy might see only darkness when they look out into the cosmos. Time, in this context, becomes a finite resource, shaped by the ever-growing distances between celestial objects. But the relationship between time and expansion goes even deeper. Some theories suggest that the stretching of space could influence the flow of time on a fundamental level. For example, in regions of the universe where space is expanding rapidly, time might appear to pass more slowly compared to regions where expansion is slower. This idea is still being explored, but it highlights how interconnected time and space truly are. The expansion of the universe isn't just a distant cosmic phenomenon. It's a reminder that time is a dynamic, ever-changing part of reality. From the Hubble constant to the stretching of light, every aspect of this expansion offers new insights into how time operates on the grandest scales. And as we continue to study this cosmic dance, we uncover even more about the mysteries of time and the universe itself. With that in mind, let's turn our attention to another mind-bending concept: quantum entanglement, and how it challenges our understanding of time. Now, let's dive into one of the most baffling phenomena in physics: quantum entanglement, and how it turns our understanding of time on its head. Quantum entanglement occurs when two particles become so deeply connected that the state of one instantly influences the state of the other, no matter how far apart they are. This connection happens faster than the speed of light, which seems to defy everything we know about time and causality. Imagine two entangled particles like a pair of dice. If you roll one and it lands on 6, the other will instantly show 6 as well, even if it's on the other side of the universe. This instant connection, often called spooky action at a distance by Einstein, suggests that information can travel between particles without any delay. But here's the catch: this phenomenon doesn't just challenge our ideas about space, it also shakes up our understanding of time. In the world of quantum mechanics, time doesn't always behave the way we expect. Experiments have shown that entangled particles can appear to communicate instantaneously, as if time doesn't exist for them. For example, in a famous experiment called the Bell test, scientists measured the properties of entangled particles separated by vast distances. The results showed that the particle states were correlated in ways that couldn't be explained by any signal traveling at the speed of light. This implies that, at the quantum level, time might not flow in the linear cause and effect way we're used to. This raises a profound question: does time even exist in the quantum realm? Some physicists suggest that entanglement might create a kind of timeless connection between particles, where past, present, and future blur together. Others propose that entanglement could be a clue to a deeper reality, where time is an emergent property rather than a fundamental feature of the universe. The implications of quantum entanglement go beyond just physics; they challenge our very perception of reality. If particles can influence each other instantaneously across vast distances, what does that mean for our understanding of cause and effect? Could entanglement hint at a universe where time is more fluid and interconnected than we ever imagined? As we continue to explore this mysterious phenomenon, one thing is clear. Quantum entanglement doesn't just push the boundaries of science, it forces us to rethink the nature of time itself. And with that, let's move on to another cosmic mystery, the Fermi paradox, and how time scales might explain why we haven't encountered alien civilizations. Now, let's shift our focus to a question that has puzzled scientists and dreamers alike. Why haven't we encountered alien civilizations? This is the heart of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the vastness of the universe and the billions of stars and planets out there, it seems almost impossible that we're alone. Yet, despite decades of searching, we've found no definitive evidence of extraterrestrial life. Could time itself hold the key to this cosmic silence? One of the most compelling explanations lies in the immense scales of time involved. The universe is roughly 13.8 billion years old, and Earth has only been around for about 4.5 billion years. Intelligent life, as we know it, has existed for a mere blink of an eye in cosmic terms. What if other civilizations arose millions or even billions of years before us? They might have flourished, advanced, and then vanished long before humans even appeared. The universe's timeline is so vast that the existence of intelligent life elsewhere could easily be out of sync with our own. Another possibility is that civilizations might not survive long enough to make contact. Technological advancement could lead to self-destruction, whether through war, environmental collapse, or other catastrophes. If this is a common fate, the window for civilizations to overlap and communicate could be incredibly narrow. Imagine two civilizations separated by just a few thousand years, a tiny fraction of cosmic time. They might never even know the other existed. Time also plays a role in the challenges of interstellar communication. Even if alien civilizations are out there, the distances between stars are so vast that signals could take thousands or millions of years to reach us. By the time a message arrives, the civilization that sent it might no longer exist. Similarly, our own signals have only been traveling through space for about a century, barely enough time to reach a handful of nearby stars. In the grand timeline of the universe, we might simply be too early or too late to connect. The Fermi paradox forces us to confront the possibility that we might be alone, or that the universe is far stranger than we imagine. It's a reminder that time isn't just a backdrop to the cosmos. It's an active player in shaping the possibilities of life and communication. As we continue to search for answers, one thing is certain. The mysteries of time and the universe are deeply intertwined, and each discovery brings us closer to understanding our place in the cosmos. With that, let's turn our attention to another mind-bending idea. What if our universe is a simulation? Could time itself be a programmed construct? That's up next. Now, let's dive into one of the most intriguing and controversial ideas in modern science. What if our universe is a simulation? This concept, known as the simulation hypothesis, suggests that everything we perceive as reality might actually be an artificial construct created by an advanced civilization or intelligence. If this is true, then time itself could be nothing more than a programmed feature of this grand simulation. Think of it like this. In a video game, time progresses according to the rules set by the programmers. The characters in the game experience time as a linear sequence of events, but from the outside, it's all just code running on a computer. If our universe is a simulation, time might work in a similar way. It could be a carefully designed framework, allowing events to unfold in a way that feels real to us, but is ultimately controlled by the underlying program. One of the key arguments for the simulation hypothesis comes from the rapid advancement of technology. As humans, we've already created virtual worlds and simulations that are becoming increasingly complex. If this trend continues, future civilizations might develop simulations so realistic that the beings inside them wouldn't even realize they're in a simulated reality. If that's possible, then it's not a huge leap to consider that we might already be living in one. But what does this mean for time? If time is a programmed construct, it might not be as fundamental as we think. In a simulation, time could be manipulated, paused, or even rewound by the creators. This raises fascinating questions about free will and determinism. Are our choices truly our own, or are they predetermined by the code of the simulation? Could the creators of the simulation observe us in real time, or even fast forward to see how our future unfolds? Some scientists and philosophers argue that if the simulation hypothesis is true, there might be glitches or errors in the program that could reveal the true nature of our reality. For example, tiny inconsistencies in the laws of physics or unexplained phenomena might be signs that we're living in a simulated world. While this idea is still speculative, it challenges us to rethink our understanding of time, reality, and existence itself. As we ponder these possibilities, it's worth considering how the simulation hypothesis connects to our earlier discussions about time. If time is a programmed construct, it might explain why it behaves in such strange and mysterious ways, from time dilation near black holes to the arrow of time dictated by entropy. It's a thought-provoking idea that blurs the line between science and philosophy, inviting us to question the very nature of our reality. With that, let's move on to another fascinating concept, the holographic principle, which suggests that our universe might be a two-dimensional projection. How does this theory redefine our understanding of time and space? That's coming up next. Now, let's shift our focus to a theory that turns our understanding of reality on its head, the holographic principle. This mind-bending idea suggests that our entire universe, with all its three-dimensional complexity, might actually be a two-dimensional projection. Imagine the universe as a giant hologram where everything we see, touch, and experience is encoded on a flat surface like a cosmic movie screen. But how does this relate to time? Let's break it down. The holographic principle stems from the study of black holes and the strange behavior of information at their event horizons. Scientists discovered that all the information about objects falling into a black hole could be encoded on its surface rather than lost forever. This led to the idea that the universe itself might operate in a similar way, with all the information about space, time, and matter being stored on a two-dimensional boundary. In this view, the three-dimensional world we experience is just a projection of that information, much like a hologram. So, what does this mean for time? If the universe is a hologram, time might not be as fundamental as we think. Instead of being a continuous flow, time could be a byproduct of how information is processed and projected from the two-dimensional surface. This challenges our traditional understanding of time as a linear, one-way progression. In a holographic universe, time might be more like a series of frames in a movie, each one encoding a moment of reality that only appears to flow when viewed in sequence. This theory also has profound implications for space. If the universe is a projection, then the vast distances between stars and galaxies might not be as real as they seem. Instead, they could be part of the holographic illusion created by the way information is encoded and projected. This could explain some of the mysteries of quantum mechanics, where particles seem to be connected across vast distances instantaneously, a phenomenon known as quantum entanglement. In a holographic universe, these connections might make more sense, as everything is fundamentally linked on the two-dimensional surface. The holographic principle doesn't just redefine time and space, it challenges us to rethink the very nature of reality. If our universe is a hologram, then what we perceive as solid, tangible, and real might be nothing more than a sophisticated projection. It's a theory that bridges the gap between quantum mechanics and general relativity, offering a new way to understand the cosmos. As we wrap up this exploration, let's take a moment to reflect on how far we've come. From the simulation hypothesis to the holographic principle, we've seen how time can be reimagined in ways that stretch the limits of our understanding. Next, we'll dive into the cosmic calendar, a tool that compresses the entire history of the universe into a single year. How does this perspective change the way we see time? That's coming up next. Now, let's zoom out and take a step back to see time on a scale that's almost impossible to grasp: the cosmic calendar. This incredible tool compresses the entire history of the universe, all 13.8 billion years, into a single year. Imagine every second of this cosmic year representing thousands, even millions of real-world years. It's a way to visualize just how vast and ancient the universe truly is. So, how does this cosmic calendar work? Let's start at the very beginning. The Big Bang, the moment our universe burst into existence, happens at the stroke of midnight on January 1st. In this timeline, the first stars and galaxies don't form until mid-January. That means for nearly 2 weeks, the universe is a dark, empty void, slowly cooling and expanding. By February, the first galaxies begin to take shape, and by March, the universe is teeming with young stars and swirling galaxies. Fast forward to August, and our own Milky Way galaxy is starting to form. But Earth doesn't even show up until September. That's right, our planet, the cradle of life, is a latecomer in the cosmic calendar. Life itself doesn't appear until late September, with simple single-celled organisms emerging in the oceans. For billions of years, life remains microscopic, slowly evolving in the background. Now, here's where it gets really mind-blowing. Dinosaurs, those iconic giants of Earth's past, don't appear until mid-December. They rule the planet for a little over a week before going extinct around December 26th. And humans, we don't show up until the very last hour of December 31st. All of recorded human history, every empire, every invention, every moment fits into the final seconds of the cosmic year. This perspective is humbling. It shows just how small and fleeting human existence is in the grand scheme of the universe, but it also highlights how much has happened in such a short time. In those final seconds, we've gone from discovering fire to exploring the stars. The cosmic calendar reminds us that while we may be a tiny part of the universe's story, we're also capable of incredible achievements. As we wrap up this section, let's take a moment to reflect on what the cosmic calendar teaches us. It's not just a tool for understanding time. It's a way to appreciate the vastness of the universe and our place within it. Next, we'll explore how time affects the search for extraterrestrial life and why the vastness of cosmic time makes this search so challenging. Stay tuned. Now, let's shift our focus to one of the most intriguing questions in science. How does time impact our search for extraterrestrial life? When we think about the vastness of the universe, it's not just space that's immense, it's time too. The cosmic calendar we just explored shows us that the universe has been around for 13.8 billion years, and life on Earth has only existed for a tiny fraction of that. So, what does this mean for finding life elsewhere? One of the biggest challenges in the search for alien life is the sheer scale of cosmic time. Imagine this: if an intelligent civilization existed on a planet thousands of light years away, the signals they send out would take thousands of years to reach us. By the time we receive them, that civilization might have already risen, flourished, and disappeared. The same goes for any signals we send out into the cosmos. Our messages could take millennia to reach another civilization, and by then, humanity might be long gone. This creates a communication gap that's almost impossible to bridge. But it's not just about the time it takes for signals to travel. The universe is constantly changing. Stars are born, stars die, and galaxies evolve. A planet that might have been habitable millions of years ago could now be a barren wasteland. Conversely, a planet that's inhospitable today might become a thriving ecosystem in the distant future. This means that even if life exists elsewhere, the chances of it existing at the same time as us are incredibly slim. It's like trying to catch a train that's already left the station or one that hasn't even arrived yet. Another factor to consider is the lifespan of civilizations. On Earth, advanced civilizations have only existed for a few thousand years, and we're already facing challenges like climate change and resource depletion. If other civilizations face similar struggles, their window of existence might be just as brief. This makes the search for extraterrestrial life even more difficult, as we're not just looking for life, we're looking for life that exists at the same time as us. Despite these challenges, scientists remain hopeful. Advances in technology, like the James Webb Space Telescope, are allowing us to peer deeper into the cosmos than ever before. We're discovering more exoplanets, planets outside our solar system, and analyzing their atmospheres for signs of life. While the vastness of cosmic time makes the search daunting, it also reminds us of the incredible possibilities that lie ahead. Who knows, one day we might find evidence of life that existed long before us, or even life that's just beginning. As we ponder the mysteries of time and the search for extraterrestrial life, let's turn our attention to another fascinating idea: how humanity's understanding of time might evolve in the future. What breakthroughs could reshape our perception of time, and how might they change the way we explore the universe? Stay with us as we dive into the next chapter of this cosmic journey. Now, let's take a moment to imagine how humanity's understanding of time might evolve in the future. As we continue to push the boundaries of science and technology, our perception of time could undergo profound transformations. One of the most exciting possibilities lies in the field of quantum physics. Scientists are already exploring how quantum mechanics challenges our traditional notions of time, suggesting that it might not be as linear or absolute as we once thought. What if, in the future, we discover ways to manipulate time at the quantum level? This could open doors to entirely new ways of experiencing and measuring time, far beyond the ticking of a clock. Advancements in space travel could also revolutionize our relationship with time. Imagine a future where humans can travel at near light speeds, experiencing time dilation firsthand. A journey that takes decades for those on Earth might feel like mere months for the travelers. This could lead to a society where time becomes a flexible concept, shaped by the speed at which we move through the universe. Colonizing other planets, each with its own unique day-night cycles and orbital periods, might further diversify our understanding of time. Living on Mars, where a day is slightly longer than on Earth, could create entirely new cultural and societal rhythms. Technology, too, has the potential to reshape our perception of time. Artificial intelligence and advanced computing could allow us to process information at speeds that make our current sense of time feel sluggish. Virtual reality might enable us to experience compressed or expanded timelines, creating simulations where hours feel like seconds or days. These innovations could blur the line between real and perceived time, challenging us to rethink what it means to live in the present. But perhaps the most profound shift will come from our growing understanding of the universe itself. As we uncover more about the nature of space-time, black holes, and the origins of the cosmos, we might discover that time is far more malleable than we ever imagined. Theories like the holographic principle or the multiverse could reveal that time operates differently in other dimensions or parallel realities. These discoveries could fundamentally alter how we view our place in the universe and the flow of time itself. As we look to the future, one thing is certain: our understanding of time is far from complete. With every scientific breakthrough and technological leap, we inch closer to unraveling its mysteries. And as we do, we might find that time, much like the universe, is full of surprises waiting to be discovered. With that in mind, let's turn our attention to the final chapter of this cosmic journey, time and the meaning of existence. How does our understanding of time shape our place in the universe, and what does it reveal about the nature of reality itself? stay with us as we explore this profound and thought-provoking question. As we reach the final chapter of our exploration, let's take a moment to reflect on the profound connection between time and the meaning of existence. Time, in all its complexity, is more than just a measure of moments. It's a framework that shapes how we perceive reality itself. From the fleeting seconds of our daily lives to the vast eons of cosmic history, time is the thread that weaves together the story of the universe and our place within it. Our understanding of time influences how we see ourselves in the grand tapestry of existence. Think about it: every decision we make, every memory we hold, and every dream we pursue is tied to our perception of time. It's what gives our lives a sense of progression, a beginning, a middle, and an end. But what if time isn't as linear as we think? What if, as some theories suggest, past, present, and future are all interconnected, existing simultaneously in ways we can't yet fully grasp? This idea challenges us to reconsider not just the nature of time, but the very essence of what it means to exist. On a cosmic scale, time reveals the fragility and wonder of our existence. The universe has been unfolding for nearly 14 billion years, and yet human life occupies only the tiniest sliver of that timeline. In the face of such vastness, it's easy to feel insignificant. But here's the twist: our ability to ponder time, to question its nature, and to seek meaning within it sets us apart. It's through this curiosity that we connect with the universe, transforming our fleeting moments into something enduring. Time also raises profound questions about purpose and legacy. If time is finite, how do we choose to spend it? Do we measure our lives in years or in the impact we leave behind? These questions remind us that time isn't just a scientific concept, it's deeply personal. It's the heartbeat of our stories, the rhythm of our relationships, and the canvas on which we paint our lives. As we stand at the intersection of science and philosophy, one thing becomes clear: time is both a mystery and a mirror. It reflects our deepest questions about existence, our place in the cosmos, and the meaning we seek in our journey through the universe. And while we may never fully unravel its secrets, the pursuit of understanding time is, in itself, a testament to the beauty and complexity of being alive. So, as we close this exploration, let's carry this thought with us: time is not just something we measure, but something we live. It's a reminder that every moment is a gift, a chance to connect, to grow, and to leave our mark on the universe. And in that realization, perhaps, lies the true meaning of existence. Thank you for joining us on this journey through the mysteries of time. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell for more mind-bending explorations of the universe. Until next time, keep wondering, keep exploring, and keep embracing the infinite possibilities of time. As we bring this journey to a close, let's take a step back and reflect on the incredible insights we've uncovered about time. From the mind-bending effects of time dilation and black holes to the mysteries of the Big Bang and the arrow of time, each fact has peeled back another layer of the universe's grand design. These revelations don't just challenge our understanding of time, they reshape how we see reality itself. Time isn't just a ticking clock. It's a dynamic, ever-changing force that bends, stretches, and even stops under the most extreme conditions. We've explored how time behaves near massive objects, how it might flow differently in parallel universes, and even how it could one day come to an end. We've seen how time connects us to the cosmos, from the tiniest particles to the vast expanse of space. And through it all, one thing has become clear: time is far more mysterious and profound than we ever imagined. But here's the real question: what does all of this mean for us? How does understanding time change the way we live, the way we think, and the way we see our place in the universe? These are questions that don't have easy answers, but they're worth asking. Because every time we delve into the mysteries of time, we're not just learning about the universe, we're learning about ourselves. So, as we wrap up, I want to leave you with this thought: what if time is the ultimate teacher? What if every second, every moment is an invitation to explore, to wonder, and to grow? The universe has given us the gift of time, and with it, the chance to leave our mark on the cosmos. Thank you for joining me on this incredible journey through the mysteries of time. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell so you never miss out on our next adventure into the unknown. And now, I'd love to hear from you. What fact about time blew your mind the most? Share your thoughts in the comments below, and let's keep the conversation going. Until next time, keep exploring, keep questioning, and keep embracing the infinite possibilities of time.